Let's talk about fugacity. Such a bad thing. No, but where is Lydia? Lydia is there. Lydia and Ben had the right idea. It's all about devolving. You have to think about it carefully. So let's work with it. So what did we do last time? So in the next few lectures, our favorite thermodynamic potential is going to be Gibbs free energy, right? And the reason it's going to be Gibbs free energy because we are interested in studying things happening at constant pressure and temperature, right? And that's the free energy that describes spontaneity, right? In constant pressure and temperature conditions. That's why it's our favorite, but all of this could be done with some other potential also, like Helmholtz free energy. So we're very interested in Gibbs. What are the natural variables for Gibbs? In PT. So pressure, temperature, number. What's the fundamental equation for Gibbs? There is always going to be a plus mu dn. It's going to be something multiplied by dp and something multiplied by dt. What comes with dp? vdp. And what comes with dt? Minus s. Okay, so this is our fundamental equation. And then we are interested in constant pressure. We are interested in what happens to a constant chemical potential as you increase the pressure at the same temperature, right? And for using that, we derived an equation last time that looked like G is equal to G naught plus RT ln P by P naught for ideal gas, right? And you can put N here, which is number of moles. If N is not there, then it's implicit that you're talking about per mole Gibbs free energy. So this was true for ideal gas. And if it's a single component system, then this becomes mu is equal to mu naught plus RT ln P by P naught. Again, ideal gas for one component ideal gas. If it's a mixture of two ideal gases like krypton on xenon, then this is not going to work, right? For one component ideal gas, this is true. Why is this true only for one component ideal gas? Because we know that G in general is mu1 n1 plus mu2 n2 plus dot 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 dot, which is the special connection of G with mu, right? A does not follow that property. So I'm trying to recap a lot of things here. And if it's a one component system, then G is equal to mu1 for one component. So G is equal to mu1 for a non-ideal system also, right? So, but it has to be one component for that. And then this relation seems so appealing that apparently it was G.N. Lewis. Does anyone here remember who was G.N. Lewis? How many of you have done undergrad in chemistry? Raise your hand if you've done undergrad in chemistry. You should know G.N. Lewis then. The Lewis, right, of Lewis. Octet rule and all those things, right? So G.N. Lewis, but I don't think it was just him. I think it's older than that. Liked this equation so much that they said, well, this is true for an ideal gas. How about we do some undergrads are happy. That's what it is, right? Okay. So if this is true for an ideal gas, for a non-ideal gas, this is not going to be true, but that's how we define the fugacity, right? We say, well, for an ideal gas, G minus G naught by nRT, right, is going to be log of P by P naught. For a non-ideal gas, it is not going to be log of P by P naught. It is going to be log of something, and that something is called fugacity divided by P naught, right? That's how we got to this. So the point where I got stuck last time, and then I realized there is something. So where is Stephen? Stephen, for example, found a paper. That made me realize that actually this argument that phi less than 1 means attractive or repulsive is not true all across pressures. So a lot of papers are actually misusing it. A lot of books are misusing it, and you'll see why. So let's work on this. So in order to, so what did we want to say? So last time we were talking about, things like you can measure G versus P, right? And if you measure G versus P for an ideal gas, it's going to look like, it will always go to minus infinity, right? G goes to minus infinity as P tends to 0 for everything, right? For an ideal gas, it's obvious because log of P goes to minus infinity as P goes to 0. But on top of that, we know that everything becomes more and more ideal as you make the pressure go to zero, right? The density becomes zero. So everything looks like that, but you could have a behavior like this, where this fugacity coefficient phi, which is defined by f by p, is more than 1. Or you could have a behavior like this, where the fugacity coefficient f by p is less than 1. And for curves like this, where there is no crossover, then my statement is true. Okay, and now we are getting into danger zone again. Shah is getting excited. He's like, he's gonna make a mistake. Find it. For situations like this, where there is no crossover, okay, then you can say that phi more than 1, let's keep the color consistent. Phi more than 1 means repulsive forces, and phi less than 1 means attractive forces. This is what we tried to prove last time, and this is going to be true only without crossover. If you have a crossover, then it's game over. It's not going to happen. Okay, so let's try to prove this. And in order to prove this, the mistake that I was making was to fixate on the pressure. But what I need to think about is the volume at the same pressure. Okay, so when I just fixate on the pressure, I'm ignoring volume. So I have to be very, very careful. And I'm talking about Gibbs free energy, right? So pressure is the control variable, right? So I fix the pressure, and then I think about how the volume changes. And this will actually lead to a nice equation in the end. So in order to do this, we are going to go back to our fundamental equation. dg is equal to v dp minus s dt plus mu dn. We are talking about constant temperature and composition. So constant temperature and composition mean dt and dn are 0. Fair? Right? So at constant temperature and composition, dg is equal to v dp. Okay. Now this equation can be written for ideal gas, or it can be written for a real gas. And when I say gas, I mean solid, liquid, anything, any material, any chemical. Okay. So for an ideal material, this will become dg ideal is equal to v ideal multiplied by dp. And we know what is v ideal. That is PV is equal to nRT, right? You can get v ideal by nRT divided by P, right? For a real gas or real chemical, this will be dg real is equal to v real multiplied by dp. So let's call this equation 1. Let's call this equation 2. And let's subtract them. Let's subtract the left-hand side and the right-hand side. Okay, so what will we get then? Then we will get d of g real minus g ideal is equal to v real minus v ideal by multiplied by dp. Now let's integrate this, where we go from 0 pressure to some pressure P. 0 pressure to some pressure P. Okay? So at 0 pressure, what is the value of G real minus G ideal? Matt, question for you. At 0 pressure, will you behave like an ideal gas or not?
Yes.
So your free energy, should it be different from the free energy of an ideal gas?
No, it should be.
It's the same. So G real minus G ideal should go to 0, right? Thanks. I was gonna bring candy because it's Halloween, but I forgot. Sorry. Have a virtual candy. So G real minus G ideal at some pressure P minus G real minus G ideal at 0 pressure, right? That's the left-hand side when we do the integration. And the right-hand side, we are going to leave as it is. We are going to leave it as 0 to P, V real minus V ideal multiplied by P, dP. And as just Matt said, this thing goes to 0 at 0 pressure, because at 0 pressure, real is ideal. There is no difference, okay? So what are we left with? We are left with G real minus G ideal. What I'm doing here is to work through the argument that I posted on Slack. It has some different notations, so I'm just expressing it in the chemistry textbook. Sometimes thermodynamics is really simple. So if I wrote a physical chemistry textbook, it would probably be 10 pages. Then it won't sell, right? So I think a lot of textbooks just like make the books very, very fat for no reason. It's really simple. And you're like, okay, G bar naught. What's the point? It's all really simple. So G real minus G ideal at some pressure, and I'm not going to write that subscript P, I will just write G real. Well, actually, let's write it. G real minus G ideal at a given pressure is now given by the integral of 0 to P V real minus V ideal multiplied by dP. Okay. Now, can we use the equations from last time? G is equal to G naught plus nRT ln P by P naught, and G is equal to G naught plus nRT ln F by P naught to substitute this one. We can, right? Because we know that G real is equal to G naught real plus nRT ln F by P naught. G ideal is equal to G naught ideal plus nRT ln P by P naught. So before one of you who is more mathematically inclined goes like, but you said P naught tends to 0, doesn't matter, it's going to cancel out, right? If I take the difference of these two. So G real minus G ideal, and I have said P naught is equal to 0. So G naught real and G naught ideal are the same, right? They are the same thing. I don't know what they are, but they are the same thing. So G real minus G ideal, therefore, is equal to nRT ln F by P naught, right? So now we put equation 4 for, what did I say? Not F by P naught, my apologies, F by P. So we put equation 4 in equation 3. What do we get? We get nRT ln of fugacity by pressure. And remember, fugacity by pressure is the fugacity coefficient, is equal to integral 0 to P V real minus V ideal by dP. And this thing is also the same as G real minus G ideal at a constant pressure. Okay, so let me write down this equation on the next page once again. So we have same equation, basically with two possible things on the left side. We can say that G real minus G ideal at a given pressure, which is the same as nRT ln F by that pressure, is equal to 0 to P V real minus V ideal multiplied by dP. So now we can think about this thing. Let's go back to the argument where we got stuck. Now we're getting into dangerous. Yeah, go ahead. What did I? He's already pissed. Tell me.
So, right, when we derive that G equal to G naught and not T, we use ideal gas, right? So now you're changing that expression.
Not for this one. This is non-ideal.
No, when we subtracted, I mean, not so we replaced V.
This is non-ideal.
And then we did the integral, right?
Not for this one. There is no integral here. This is the magic of fugacity. There is no integral here. You say for anything, what am I pointing at? This one, yeah. G real, you can always measure for some chemical, G real minus G naught real, right? And you divide it by nRT, and the log of that, the exponential of that is fugacity. There is no integration here. Integration came for this one. This was without integration. We saw the equation that was the magic of, not magic, but that is why we led to fugacity, right? This equation comes from integration. The one I just made a black star. The one on the bottom has nothing to do with integration. It's just like, I want it to look like what the ideal thing looks like. So there is no integration, no ideal. Very general. So let's look at this one now. And now think about if attractive forces dominated, and this is why I said the argument holds without crossover, dominated from 0 to P. Lydia, I'm going to look at you. If attractive forces dominated as you ramp up the pressure, okay, you're ramping up the pressure, at any given pressure, you are thinking, you know that attractive forces are dominating. What effect will it have on the volume of the system? It will shrink, right? you're all very happy with each other. I can patch you up in that corner. You will be very happy, right? So if attractive force is dominated from 0 to P, then V real should be lower than V ideal, right? At every pressure. That's why I said no crossover. If you have crossover, then this story becomes different. So what does this mean? It means that this integral is now going to be a negative number, right? So equation number 5 can also be written as F is equal to P multiplied by log of F by P is equal to 1 by e to the power 1 by nRT integral 0 to P V real minus V ideal multiplied by dt, right? I think I got that right. So if this thing is negative, then what is e to the power negative? That's a number smaller than 1, right? E to the power 0 is 1. E to the power negative is a smaller number smaller than 1. Attractive forces imply that F is smaller than P. The fugacity is smaller than P. And what was the fugacity coefficient? That was F by P. That is less than 1. Okay? And same idea applies for similar for repulsive forces. And I said I will give this a bonus problem, even though I did it here, so I will do it again. But repulsive forces, you have to just work through that argument again. Okay, so I want you to do that in homework. Okay, if you have a crossover, clearly this fails. So if you so that makes fugacity a bit less attractive, because if there's a crossover, you cannot anymore tell whether it's attractive or repulsive forces. But what I do like about equation 5 is the first part. If I look at G real minus G ideal as a function of pressure, that is going to be 0 to P V real minus V ideal dP. I think this is an amazing equation. Can anyone tell me why? First, tell me why. Yeah. I asked you a question first. It's staying queue. You tell me now. Why? Why am I so excited about this equation?
Yeah, I don't know how to do that experimentally.
Experimentally, you can measure the volume of something, right? It's probably going to be easier at a given pressure. So, okay, let's work on this term by term. V ideal at a given pressure. Do you know how to measure that? And temperature is constant, T. Right?
So, I mean, we use the ideal gas.
Ideal gas law. Okay, so V ideal we can get from, did I miss an NRT or anything? No, probably not. So ideal gas law tells me, and V real I can measure in experiment, right? Volume. And if you say, I don't know how to measure, let's think about, probably it's a nicer thing to measure than the entropy, right? We can agree on that you can measure the volume. So this you can measure. So if you have a real material for which you don't know what's going on, you can measure the right side of this equation by just measuring the volume of that material, right? So it gives you a way to calculate the G real, except you also need to know the G ideal at a constant pressure. Does anyone here remember how to get that? Not Shah, and I will come back to your question, Shah. How do I get G? So if I had an easy formula for G ideal as a function of pressure, then this equation is fantastic, right? All I need to do is to take my chemical, measure the volume as a function of pressure, subtract out the G ideal, and I get the G real. And once I have the G real, well, the whole world is mine now, right? I know it's a state function. I can manipulate it. I can talk about whatever. Venkat, how do I get G ideal? Which one? So what is the formula for G? What is G? In terms of other things? H minus Ts, right? So H minus Ts. What is H? H is U plus PV minus Ts, right? What is U for an ideal gas? Who said 0? Not 0. Good thing I didn't say who said 0. It's 3 by 2 nRT. Equipartition holds true, right? What is PV for an ideal gas? nRT. Murray? nRT, right? Okay. Always check with Murray on ideal gas law. Tricky one. What is S for an ideal gas? Anyone remembers? That's the name, but what is the value? Huh?
B times.
It's really simple. It's if you want to remember forget about the coefficients, but the dependence, it depends only on volume. And it looks just like all of your favorite entropy formula, Boltzmann's formula. Boltzmann's formula says S is equal to K log W. And for an ideal gas, the entropy is S is equal to K log volume, multiplied by some coefficients, that something, minus T, some coefficient that you can check in this formula that we did, multiplied by log of volume. So we have an analytical expression for the entropy of an ideal gas, right? So that's why this equation is so powerful. If you can measure the volume as a function of pressure, we can go back and get this. Any questions on this? And before Shah's question, maybe he addressed this already. Yeah, Anjali.
Can you explain again why we can assume that G naught and the rho of an ideal is the same? Is it like actually zero pressure or is it
Zero pressure.
just
I said the pressure equal to zero. If P naught was not zero, then it won't be true. Only at zero pressure, right? Because everything goes to minus infinity. You have sort of divergence if you're careful about it. Okay, any more questions? Shah, you still have the question?
I think go back one slide. So yeah, so at zero temperature, we assume that
Zero temperature or
I mean, G real and
zero pressure?
zero pressure.
Yes.
The two are the same. But what about no, I'm good.
I'm so happy. Okay, I can move forward. So we did our fugacity. Now we are going to go to one of the parts of thermodynamics, which I like a lot, which is phase diagrams. And we are going to spend a lot of time on phase diagrams. These are fundamental. So I did my undergraduate degree in a very old school subject known as metallurgical engineering. This is how you make iron and steel and things like that. And their thermodynamics was critical, right? But it's also critical in many, many things. And it's coming back in fashion in biology due to liquid-liquid phase separation and problems like that. And all these biologists who never took classes on phase diagrams, I find them writing papers which are wrong because they just don't know how to talk about phase diagrams. So I used to not do this in that much detail, but as I have seen like things like liquid-liquid phase separation and other things also, I feel this is your only avenue to really think about phase diagrams carefully, or you will never study it and just write wrong papers. And that will make me very sad. So phase diagrams are one way to think about it, that they are sort of maps. They are thermodynamic maps. What do I mean by that? So imagine an axis, and this could be a three-dimensional. We will talk about three-dimensional phase diagrams, how to draw them. The easy way would be to carry an object, right? But I will show you how to draw a three-dimensional phase diagram in 2D. That's known as a Gibbs triangle. But for now, let's just consider two-dimensional phase diagrams. On the left axis, you have some intensive quantity. So that's quite general, that phase diagram. These are maps in intensive quantities, okay? Intensive quantity 1. And on the y-axis, you have intensive quantity 2, okay? The phase diagrams answer the question is that for any given value, any pair of value for these intensive quantities, and if you had a high dimensional phase diagram, then more than 2 intensive quantities, what is the most stable phase? That is the question we are going to address, okay? We will develop machinery to do this, and we will be careful about what do we mean by phase and things like that. So let me give you some examples of phase diagram before we progress further. The most important one is water, right? Water phase diagram dictates how life is. Otherwise, life would have been very different. So water phase diagram can be drawn in many spaces. Typically, the 2 intensive quantities that you look for that you use in a water phase diagram are pressure and temperature, okay? And in this water phase diagram, you draw a line that looks like this, the other one looks like this, and the third one looks like this. Over here, the solid phase is most stable. Over here, the liquid phase is most stable. Over here, the vapor phase is most stable, okay? This point over here is known as the critical point, and we will understand what exactly that means. This point over here is known as the triple point, at which 3 phases coexist. If you were to zoom in, you will find that inside the solid, there is actually a whole different map that exists of different forms of ice. There are something like 15 forms of ice that can form. And on in extrasolar environments, we normally don't form ice in the form that we see it on planet Earth. Those are in different forms. So these are very critical if we want to understand if life exists in extraterrestrial planets, right? So when you send like a rover or a rock probe or something to some comet or things like that, you will probably not be and you are looking for water. You're not looking for water in its liquid form, most likely. You're looking for water in some solid form, which is very different from the solid form of water that exists on planet, right? So that's why a lot of people do experiments on water in very, very high pressure and very, very low temperature and try to create those forms over here. And it's likely that water has not just 15 forms in ice, it's probably way more than that. 5, 10 years, 20 years ago, there was a huge controversy, especially in the last 10 years, about liquid water. Turns out that at very, very high pressure, water itself can undergo liquid-liquid phase separation, and it exists as a low-density liquid and as a high-density liquid. And in your next semester, you will be studying from a book by David Chandler, and who was a very famous StatMech expert. He insisted till his death that no, this is wrong. Water can exist only as one liquid form. And there is another famous scientist, Pablo de Benedetti, who is the dean of research at Princeton. He insisted that no, it exists as 2 liquid forms, and they had a bitter fight. There is an article in Physics Today, I will post it on Slack, the war over supercooled water. And in the end, Chandler was wrong. But that was yeah. So, it's rich, and we want to understand what's going on. And water conferences are always the most intense conferences. People fight over water all the time. Anyway, so let's get back. So this is water. Another phase diagram, which is very important, that in my undergrad, I used to have to remember by memory. I will draw it. I actually never remember. I would just draw it in my hand. It was terrible. There's no way I could remember it. And I will tell you a story about this phase diagram. This is the iron-carbon phase diagram. Does anyone here know why is carbon so important for iron? What does carbon do to iron? Huh? I heard. Steel. The difference between steel and iron is carbon, or what else did you add, right? And Iron Age came way before any other age, right? When was the Iron Age? Something like 10th century or 11th century AD and things like that. And in India, where I'm from, there is a pillar known as the Iron Pillar in New Delhi, which is 1,000 years old, and it still does not have any rust on it. Because normally iron rusts, right? So once you start adding carbon, it stops rusting, right? So people want to understand what is the phase diagram of iron, and I will just draw this phase diagram to show you how complicated these things can look. And in iron-carbon phase diagram, the intensive quantities are different. Normally, the y-axis tends to be temperature. The x-axis tends to be percentage of carbon. And then it looks like this. And you don't have to draw this. I'm not going to quiz you on this. After a few classes, you will be able to understand what exactly is the meaning of these curves. Yeah, I used to have to remember this by memory. I think I might even be making a mistake here. It goes on and on. Huh? Why does what? Don't draw it. This is okay. The point is, each of these is a different phase. One of them corresponds to magnetic iron. One of them corresponds to body-centered cubic iron. And the percentage that we are talking about is very small here, something like 1% or even smaller. And even though the phase diagram for iron was not measured experimentally until like 200 years ago or something, there are people who work in steel plants who can just look at the color of the flame and tell you what percentage carbon is there, because it's such an old industry. Anyway, and I will explain to you what is the meaning of things like this and how do we understand how they come from the Gibbs free energy. So we will be understanding and things like that, okay? So, but let's now, so this is just an example of what I think these are the two most important phase diagrams for human life. The water phase diagram and the iron-carbon phase diagram. And these two have really decided who we are and how we live and everything. So before we go any further, we have to define what do we mean exactly by a phase. So And I also want to make a point that we are talking about equilibrium phase diagram. So we are talking about what happens when equilibrium is reached. There is no sense in talking about a phase diagram which is out of equilibrium. It doesn't make any sense. Thermodynamics does not apply. Okay. So I will write down the definition of phase explicitly. So phase is a region of space, physical space, throughout which all properties of a material or a chemical are uniform. What do I mean by property? I mean things like density, magnetization, chemical composition, refractive index, whatever physical property you want to think of, it's uniform. Okay. Let's try to understand some examples of phase. Let's think about, since we were just talking about iron, let's think about a pure element. Okay, some pure element. Let's say sodium. Okay. Can sodium exist? It's pure element. Can it exist in one phase only, or can it have more than two phases? What are the phases of sodium you can think of? Solid, liquid, gas, right? That's already the first three that you can think of, just like we saw for water, right? So already this can have solid, liquid, or gas. But inside each of them, if sodium is solid, do you know for sure that it is the same phase, or can it be different?
It could adopt a different crystal structure.
Crystal structure, exactly, right? So solid could be different crystal structures. Do you know, can you tell me, Sanjana, some of the crystal structures sodium might or might not take? What is the most closely packed crystal structure?
FCC.
FCC. And same close packing as that one. There is another one which has exactly the same density. HCP. Then which is the crystal structure which is less packed than these?
Body center.
Body centered cubic. Does anyone know what is the packing efficiency of FCC and HCP? It's around 80%, something like it, 78%. Can you prove this? That this is the most closely packed structure you can get? So that's known as Kepler's problem. You know, Kepler, the famous scientist. So Kepler was the first person to conjecture this, that if you pack things in a face-centered cubic arrangement, so that looks something like this. So if you have a stack of oranges, you pack them like this. Every layer will look like this. It's like a hexagonal thing. And the next layer, you pack like this, okay? That becomes a face-centered cubic arrangement, as opposed to a body-centered arrangement, where if you have a cube, it's going to look like you have an atom here, 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 on each corner, and one in the middle. And these two are not same phase. Different crystal structure is different phase. So Kepler was the first person who conjectured that this is the highest packing efficiency that you can achieve, but he was not able to prove it. The proof actually came in 1998, and it used a computer. There is still no purely mathematical proof. So people were able to do it with a computer, and yeah, I mean, I can tell you more about it if you're interested. This is very important in designing anti-spam software. Apparently in higher dimensionals, you can achieve higher packing. So it's a crazy world. So let's get back to this. So solid can take different crystal structures, right? And they are different phases. So that's something to keep in mind. So the same element, sodium, can take solid, liquid, gas. That's already three phases. And inside solid or liquid or gas, you can have different phases, right? So now let's go to another limit. Instead of sodium, now let's think about a combination of two elements, right? So one of the combination of two elements that you can think of is copper plus zinc. Does anyone know why there is a name for copper and zinc, copper plus zinc? Brass, there you go. So brass, even though it has copper plus zinc, that doesn't mean it has to be two phases. It could take a different crystal structure and then become different phases, right? But just because you have two elements, it does not mean you're going to have two phases. Is generally one phase, and I don't know which one it is. It is phase-centered or something like that, right? So you have to look carefully. So just because you have more elements involved, it doesn't mean it's more than one phases. And just because you have only one element involved, it does not mean there is only one phase, right? So you have to go and see what is the crystal structure and things like that, okay? Any questions about this? So that's our phase. That's the first definition I wanted to tell you about. The second definition that I wanted to tell you about is component.
What does it has to do with,
Say again.
what does this like, different crystallization structures, like, oh, what does it have to do with? Like,
With what?
with thermodynamics.
With thermo, everything. In
But what's,
so let's think about, you are in biophysics, right? A protein. Proteins, how do you find out the secondary structure of a protein? By crystallizing it. There you go. So you're talking about free energies of protein in a specific form. If you don't do thermo, you will be like, I don't know how to do it.
I see. So this one for one.
Yeah. So in other words, most of the things that we are interested in studying as scientists, they exist in crystalline forms, right? Not everything. There are some things that exist in other forms also. Do you know what examples are there? Polymers, right? A polymer might not be crystalline. A glass is not crystalline. They are the hardest systems to study. If you can stay away from polymers and glasses, they're really, really complicated. You know, they're very complicated. So if you can crystallize something, you can certainly measure it in a more controllable manner and talk about it. And as soon as you have crystallized it, you need thermodynamics give you a language to talk about it. That's why we are doing it. Okay. And crystal structure is just one example of different phases. You will see many, many more examples. Okay. So component. Component is a word we use casually, but let's be a bit more precise about what component means, okay? And it's different from phase. So I will first write down the definition. Component is a chemically independent constituent of a system. Normally, the number of phases of a system are denoted by P, okay? And the number of components in a system are denoted by C. So what we are doing with all of this is to get ready for the Gibbs phase rule, which is, I think, one of the most, one of my favorite equations was the Clausius inequality, right? And Gibbs phase rule is up there for me. It's like one of the triumphs of thermodynamics, like something like that exists. So component is a chemically independent constituent of a system. So chemically independent is a key word here, okay? Let's think about water. How many components is water? Let's say you have water in which ice is, this is just liquid water. Let's start with liquid water. How many components is this?
One component.
Liquid water could be one component. If there is ice floating on top of it, how many components is that? It still could be one component, right? It's two phases now, right? You have liquid water and solid ice, but it is still, it could be one component or two component. When could water be more than one component?
Yeah, solution to it.
Even simpler, pure water. Even simpler. Autoionization, right? Most of the time water, I mean, that's my simpler. Most of the time water exists as hydronium and hydroxyl, right? So if water is existing as H3O plus OH minus, how many components do you have here? So let me actually write it down one by one. So pure water without autoionization, number of components is equal to 1, right? If you have autoionization going on H3O plus OH minus. How many components do we have now? Lydia says 3. Do we all agree with Lydia? I don't agree with Lydia because I wrote down chemically independent. And notice I also wrote down the equilibrium sign. So they are constrained. If you know the amount of H3O plus, right? Water has a well-defined equilibrium constant. So if you knew the amount of H3O plus, you cannot change OH minus and H plus arbitrarily. So there is 1 degree of information is taken down. So the number of chemically independent components is actually 2. Okay, so this becomes complicated. And if you look up textbook by like Atkins and stuff, it's 2 or 3 pages, which is very confusing. In this course, I'm going to specify for you what is the number of components. Okay, I'm not going to have you calculate that. But I just want to keep in mind that if you have 3 independent species existing, that does not mean it's always going to be 3 component system. You have to think about equilibrium and things like that. But all the problems, I will tell you, it's a 1 component system or a 2 component system or a 3 component system. Okay. So we have defined 2 things. Now the third thing that I need to define before I get to Gibbs phase rule is this concept of degrees of freedom. This one is denoted by F. Okay. Degrees of freedom is the number of intensive quantities such as pressure, temperature, mole fractions, not number of moles, but mole fractions, that can be independently varied. Okay. So this is the part that can be a little bit more confusing. So let me try to explain this to you through our water phase diagram, which we are going to revisit many, many times. Okay. So water phase diagram, you have pressure and temperature. And you have 3 things like this. You have solid, liquid, and vapor. So this is pure water, okay? No auto ionization or anything like that going on. In the vapor phase, how many degrees of freedom do I have? For vapor to exist, can I specify pressure and temperature independently? I can, right? It could be this pressure over here in black and that particular temperature, or it could be this pressure or temperature up here, right? It could be any of these. So inside this region, the number of degrees of freedom is equal to 2. You can vary pressure and temperature independently, okay? How about the liquid vapor coexistence line? Can I vary pressure and temperature independently along this line? I cannot, right? Because it's a line. Anytime you tell me the value of the pressure, I have a constrained value of the temperature and vice versa, right? So along this line, degree of freedom is equal to 2. How about the triple point of water? What is the degree of freedom here? Previous one was, oh yeah, this is 1. Triple point? 0, it's a point, I have no degrees of freedom. And turns out, so in this one, so a question I want to ask all of you right now is, why does water only have a triple point? Why there is no quadruple point? Why can't we have 4 phases of water existing at the same pressure and temperature? So you might say, well, if I look at this phase diagram, you have only 3 phases, right? Solid, liquid, and vapor. So how you don't have any 4th phase? But then I also told you that ice can exist in different forms, right? So let me open up the water phase diagram to show you with ice. There we go. Looks complicated, right? So you have the vapor phase over, this is the vapor phase. That's your triple point, right? All 3 phases exist. So in this region, the degree of freedom is 2. Along this line, the degree of freedom is 1, right? So in other words, what does What does this thing tell you? This tells you the boiling point, right? At a constant pressure, if you're increasing the temperature, you know the boiling point, right? And this is the triple point. But water has all these other phases also, right? Notice you never have a quadruple point. Even though you have these 15 phases, you can only have 3 phases existing at the same point. In order for more than 3 phases to exist at the same point, you will either have to have autoionization going on, or you will need to have impure water. And that is what Gibbs phase rule will show us why that is the case. Okay. So this phase diagram goes up to 15th phase of ice. And I'm pretty sure, I think 15th phase is found on Saturn. Ice 15 is is found on Saturn. And yeah, there all the water is mostly ice 15. So if you wanted to do, going back to Maria Delia, if you were a biophysics student on Saturn, you would be studying about ice 15. I see. Okay, but you're on Earth, so it's okay. So, so that's our degrees of freedom, okay? So now I can tell you Gibbs phase rule, and then we will come back to proving it. Gibbs phase rule, which was first proved by Gibbs, as the name says that the number of degrees of freedom of a system is equal to number of components minus number of phases plus 2. This applies only to systems in equilibrium, right? That is something I have to keep reminding. Most of the times when you see violation of Gibbs phase rule, it means you are not in equilibrium. And the way we are doing thermodynamics, when we prove Gibbs phase rule, I'm actually going to prove the easy part, and I will have you do the harder part in the homework, which will be released day after tomorrow on Thursday. You will do it for the general case, and you will see that you don't need much to prove this, except the postulates. That's it. Everything follows from postulates. I mean, it's not obvious, but step by step, starting from postulates, you can prove Gibbs phase rule, which is kind of amazing. Okay, so I'm going to prove Gibbs phase rule for a very, very easy case, which is a one component system. Okay.
What is P here then?
P is the number of phases, not to be confused with pressure. Number of components, and I will prove and give you examples of this for water. That will make sense more. This is number of phases. Some textbooks provide Gibbs phase rule as C minus P plus 1, and that depends on how they are talking about pressure and temperature, but this is what we are going to use. Okay, so let's prove this for a one component system and also try to develop intuition for this by looking at water. Okay, again, so the water phase diagram will keep coming so many times. So pressure and temperature. This is solid. I didn't get it wrong, right? Sometimes I make mistakes. Liquid. Oh, I had it right. And vapor. The first question about the water phase diagram is, you see that the slope of the solid liquid curve, it faces towards the left. And water is the only phase diagram in which this curve faces left. Almost everything else, this curve faces right. And the practical implication of this curve facing left, as we are going to see, is that ice is lighter than water. Between water at 0 to 4 degrees Celsius is heavier than ice. So ice floats on water, which is crucial to life existing. And there is one more chemical, I think, which has a similar behavior. That's known as helium-3. And there it's all complicated reasons at all. It's apparently a sort of superconductor. But apart from helium-3 and water, most phase diagrams are quite well behaved. But we will look at this one and try to understand Gibbs phase rule. So proof of Gibbs phase rule for one component system. General proof in homework. And that's my grinning face. It's a bit messy. So you will have type 2 fun. So one component system. What is the value of C? 1. Good. You're awake. So what do we want to prove then? We want to prove that F is equal to 3 minus P, right? That the number of degrees of freedom is 3 minus the number of phases. Does this make sense? How many degrees of freedom do we have in the vapor region? 2. And how many phases do we have? 1. So it's consistent, right? In this phase, in this region, 2 is equal to 3 minus, no, what did I do? 3 minus 1, sorry. So F is equal to 2, and this is the number of phases, right? If I go along the line, how many degrees of freedom do I have? 1, right? You can just move along a straight line. If you know pressure, you know temperature. You cannot change both of them together. So along the line, the number of degrees of freedom is equal to 1. And what is the value of P along the line? 2 phases are coexisting, right? Liquid and vapor are coexisting. So 1 is equal to 3 minus 2. So F and P, right? And again, it's true. If you go to the triple point, how many phases do we have here? 3. It's a triple point, right? So 3 minus 3 is equal to how much? 0. No degree of freedom. It's set, right? So you can see water phase diagram is consistent with this. So how do we prove this for a one component system? We will start carefully. We will start with one component and one phase. So C is equal to 1, P is equal to 1. For a one component, one phase system, you can vary pressure and temperature together. There is no constraint that you know of coming from thermodynamics, right? We can vary pressure and temperature independently. So if it's pure water existing as liquid, it can exist as liquid as 1 atmosphere and 300 Kelvin. It can exist as liquid as 2 atmosphere and 310 Kelvin, right? You can vary both of those things independently. So if you can vary both P and T independently, what is the number of degrees of freedom? That is equal to 2, right? And 2 is equal to 3 minus 1 is equal to 3 minus P. So the proof is almost trivially correct for one component, one phase system. This is quite easy. It becomes slightly complicated when we go to one component, two phase system. And that's where we will understand why is it that the number of degrees of freedom for a one component, two phase system actually go down. So one component, again, just like water, but two phase. Now you have liquid and vapor maybe coexisting together along that line. What is C now is equal to 1. What is P is equal to 2, right? Go ahead.
So when Gibbs came up with this formula, it was before the time that Einstein had the Brownian motion. So how,
There were no atoms.
yeah, exactly. So how he were able to talk about components when nobody believed?
Components can be talked about without atom, right? This is coffee. It's a one component system. It's not component. It's complicated waves inside it. I don't care. So component is distinct from atom.
Because for example, in water, you were talking about the ionization, something that was.
But he wasn't really looking at water, right? I mean, people were thinking in very funky ways back then, right? Until 1905, no one believed atoms. Very few people believed atoms. Think about it. I can find Gibbs's original paper. When was Gibbs? I have Gibbs's book on thermodynamics in my office. Gibbs is not as old as you think. Don't confuse him with Carnot.
No, he died like beginning of the.
Yeah, but he was not that far behind Einstein. Carnot was 200 years ago. So I don't know if Gibbs was leaning towards the atomic picture or not. It's a good question. Maybe he was inspired by that. The Germans, they were very divided. That's why Einstein also, there were many reasons why Einstein escaped the United States. But one of them was like, yeah, anyway, let's not go there. So this is a one component, one phase system. Now, one component, two phases, we would like to show F is equal to C minus P plus 2, right? That's Gibbs phase rule, right? That's what we want to prove, that it's valid in this. So we are proving it case by case, right? Today in class, I'm doing one component, one phase, two phase, three phase, four phase. In your homework, you will do K components, any number of phases, okay? So I would like to show C minus P plus 2. So 1 minus 2 plus 2 equal to 1. So I want to show that here you cannot vary pressure and temperature independently. How do I prove this? Why is it that the number of degrees of freedom went down? So if two phases are in equilibrium, their chemical potentials must be equal. This is a two-line proof, which I'm going to do in a little bit. Okay, just take my word on this for now. I wanted to work through Gibbs phase rule and then come back to this proof. Okay. In other words, the chemical potential of phase alpha as a function of pressure and temperature should be equal to the chemical potential of phase beta as a function of pressure and temperature. This kind of, you can see from this why chemical potential has the word potential in it, right? What does gravitational potential mean? Gravitational potential means the direction in which you fall, right? What does electric potential mean? The direction in which charge moves, right? So chemical potential is the direction in which matter moves. If alpha and beta are in chemical equilibrium, their chemical potentials are equal, and matter, the one component system, is not going to move from alpha to beta. Okay, that's the idea. And we are going to prove this mathematically in just a bit. This is a constraint, right? Mu is a function of pressure and temperature. We don't know what is this function. It's a very complicated function. Maybe mu looks like p to the power 5 minus p to the power 44 plus blah, blah, blah. It's some function. So if you know the pressure and temperature, they are connected through this equation. We don't know what is this equation, but it exists, right? This is the condition for. So this condition can also be known as second law of thermodynamics for phases. That if two things are in chemical equilibrium, if two phases are in equilibrium, their chemical potentials must be equal. Okay? And we are going to prove this in just a moment mathematically. So suddenly you have a constraint on pressure and temperature. It will, for example, this could look like P square plus AP square plus BT cube is equal to CP4 plus DT5. I don't know. It's some function. I don't know what is that function, right? And you have to fit the value of A and B from experiment. You happen to know it by using some equation, Gibbs-Helmholtz or whatever, right? You were able to find it. So this is a constraint on pressure and temperature. They are no longer, they can be varied independently, right? So therefore, pressure and temperature are connected and cannot be varied independently. Therefore, number of degrees of freedom goes down from 2 to 1 and becomes 1, right? You have one constraint. You have 2 degrees of freedom, pressure and temperature. If it was a multi-component system, then you would have had more degrees of freedom. And that is why your homework problem will be slightly harder. You will have to think about that, right? But here it's one component system. All you can change is pressure and temperature. And now one of them went down. So again, we are able to prove it for one component, two phases. You have a question? No, okay, good. Let's go to one component, three phases. Here, Gibbs phase rule is going to look like F is equal to C minus P plus 2. So one component meaning 1, number of phases meaning 3 plus 2, that is 0. So we want to show that for one component, three phases, there is no degree of freedom. Pressure and temperature must be a well-defined point, triple point. So this shows why water has a triple point. How do we do this? Same thing. Let's call the phases alpha, beta, and gamma. And you had 2 degrees of freedom you can vary, P and T. But you again have to write down now 3 phases exist in equilibrium. if three things exist in equilibrium, how many equations do I need to write? What do you think? Okay, yeah. Let me repeat, if three phases exist in equilibrium, how many equations do I need to write?
Still probably one.
Or two or three? Let me rephrase it in more common sense language. If you have the same amount of money as Sanjana, and I have the same amount of money as Sanjana, let's call the money you have as A, and the money she has as B, and the money I have as C. How many equations do I need to write to express this? 3 or 2 or 1? 2. Why? 2 already does it, right? A is equal to B, B is equal to C. There is no need to go and write C is equal to A. In maths, that is known as the transitive relation, right? It's already implied. Okay, that's fine. So in this case, it will look like, this is a subtle point. So mu alpha, and when you go back and look at it, you might again get confused at home. So we are going to write mu alpha PT is equal to mu beta as a function of pressure temperature is equal to mu gamma as a function of pressure and temperature. Even though you have three variables, this is not three equations, this is two equations, right? You have two equalities. So the number of degrees of freedom goes from F equal to 2 to 2 minus 2 is equal to 0. Now we can already prove why water cannot have 4 phases. If we had 4 phases, how many equations would we have? 3, right? Mu alpha is equal to mu beta is equal to mu gamma is equal to mu delta, and we started with F is equal to 2. If you subtract 3 from 2, how many degrees of freedom you get? -1. That's kind of crazy, right? That's like science fiction. You don't want to go there. I'll pause for a moment. I'll go to the next page. Okay, yeah, go ahead. Uh-huh.
So if you have, let's say, 4 phases, hypothetically, you say that there is -1 degree of freedom, that is from the equation. But what if one of those equations is like degenerate? You could have the same solution that is like multiple.
You could have some limiting cases, but it's generally not possible. Let me think more about that, but I don't think it happens. Yeah, you could have some degeneracy. That's a good one. Let me send me a message on Slack, okay? I want to think about that. I will forget. So one component, and it's going to be exceptionally hard because it has to happen at like different pressures and temperatures and stuff. It will be some special case, but who knows?
Yeah, if you're lucky.
If you're lucky, but it won't be general. So if one component 4 phases, alpha, beta, gamma, delta, we will have mu alpha is equal to mu beta is equal to mu gamma is equal to mu delta, or 3 equations, right? And at best, we could have had 2 degrees of freedom in a one component system. That is pressure and temperature. 2 minus 3 is equal to -1, right? Therefore, one component system at a given pressure and temperature can at max have a triple point. If you are going to have a quadruple point, you need to have a 2-component system. So in the homework, you are going to prove this for the general K component case. If proof is online, you can just copy, but that will make me sad. Please try to work through the proof and understand what it means, okay? You will have such equations, not just for, you will have to think about I is equal to 1. The different components will have to show up in the superscripts, okay? I is equal to 1, I is equal to 2, I is equal to 3. You will have a matrix of equations and you'll have to think a bit more carefully. But again, you will reach, so this is the component number. That's what you will have to think about. Again, you will reach the same conclusion. So you can prove it in a very general case. In order to prove this, however, we assume that chemical potential, if 2 phases are in equilibrium, their chemical potentials must be equal. So the reason I am doing this after going through the Gibbs phase rule is because next time what we are going to do is to derive equations for these curves. How exactly do these curves behave? You will be able to write down equations for that. Those are known as Clapeyron equations and Clausius-Clapeyron equations. And there again, we will be starting with this chemical potential. So that's why I wanted to do it now, so I can recap this proof next time and then start with Clapeyron equation. So any questions about this? Okay. So we want to show proof of second law of thermo for phases. And I want to do it on one page, so I'll just go to the next page. Do it there. So let's imagine we have a box. And in this box, we have phase alpha on the left side and phase beta on the right side, okay? And I will show you the proof for a one component system. You could generalize it for two component system. It just doesn't matter, okay? It's very similar proof, as long as you assume constant composition. So, let me actually show it to you for two components. So let's say you have black dots on both sides, which correspond to some species 1, and red dots on both sides, which correspond to some species 2. So is equal to species 2 is equal to species 1. And let's say there are many, many more species, okay? And number of species is the number of components in the system. We have taken care of all chemical reactions that can happen. So let's focus on species I equal to 1 at constant temperature and pressure. And you can do it for other species also. It's the same thing, same proof. There is no difference. Let's transfer dN1 moles of species 1 from phase alpha to phase beta. We are talking about equilibrium at constant temperature and pressure. Our state function for this is Gibbs free energy, right? If this is truly at equilibrium, what does equilibrium mean? Again, let's go back to Sanjana. Today she is my model. So let's say Sanjana and I are in financial equilibrium. We are not, but let's say we are. It means that I could give $5 to her and she could give $5 to me, and it's not going to change the configuration of the world, right? Money can flow in either direction, right? So if chemical equilibrium exists in constant temperature and pressure, it means that the effect of transferring a little bit of species 1 from alpha to beta, dg should be equal to 0, right? If dg was negative, it means we are not in equilibrium. It means that I like to take money from Sanjana. And that's not equilibrium, right? It's bad. I should not do that anyway. I will never take money from you, just to be clear. So for this to be reversible, dg should be equal to 0, right? Because we are working at constant temperature and pressure. And I wanted to do phase diagrams first because I wanted to show you some practical aspects of thermodynamics. I will come back in a few weeks to Legendre transform and how these state functions are connected to each other, right? But for now, I wanted to go to some practical bits. So dg is equal to 0. Now, where does dg come from? dg comes from dg of phase alpha, right? Whatever alpha free energy change and free energy due to phase beta, right? Both of them should be equal to 0. What is the fundamental equation for dg? Now you should all remember it very, very clearly. dg is equal to minus s dt plus mu dn. What is the fundamental equation for dE? Plus mu dn. These are the two you should try to remember. The others you will forget, but these two are really important, right? This one is very easy. It's integrated first and second law. The dg is a bit harder, but it just shows up so many times. It's worth remembering. So dg alpha plus dg beta is equal to 0. we are talking about constant pressure. So dP is equal to 0. We are talking about constant temperature. So dt is equal to 0, right? Constant P and T means dP is equal to dt is equal to 0. Therefore, dg is really coming from mu dn, right? So if dg is coming from mu dn, what is dg alpha? That is going to be the chemical potential of species 1 in phase alpha, right? So dg, in other words, dg alpha is equal to mu alpha dn, dg beta is equal to mu beta dn, both for chemical species 1, right? So we can now write down, what's the equation number? We can give it some very large equation number. That's where we are safe. Let's call it equation number 11. Equation 11. So equation 11 implies mu1 alpha multiplied by dn. If n1 moles, if dn1 moles were lost from phase alpha, then that is going to be negative for phase alpha, right? So this is minus dn1 plus mu1 beta, chemical potential of species 1 in phase beta, multiplied by plus dn1 is equal to 0, right? Or in other words, mu1 alpha minus mu1 beta multiplied by dn1 is equal to 0. And this equation is true for any value of dn1, right? Millimole, very, very small, like 1 mole is how lots and lots of atoms, right? So let's say 10 to the power minus 23 of a mole, or 2 into 10 to the power minus 23 of a mole, or 3 into 10 to the power minus 3. We did not say what dn1 it is, right? So if this equation is to be true for all dn1, true for all small dn1, right? If we are talking, if again Sanjana gives me $1 million, unless she's a trillionaire, Jeff Bezos or something, that's not going to be in equilibrium, right? So it has to be some small amount of change, right? So if it is true for all small values of dn1, what does that mean? That means mu1 alpha is equal to mu1 beta, right? Is this clear? Another problem in your homework is going to be to take this and show that matter will move from high mu1 alpha to low mu1 beta. It's just like potential. Again, you can show, just like you did for temperature, you showed that the Gibbs free energy goes down or up. That's how you will prove it, okay? So this is where I wanted to stop today. Any questions? Good. So next time, please go through this proof. Next time we are going to start with this. Gibbs phase rule you will visit in the homework. And we are making good progress. I am, however, will have to do one extra class. It will be on Zoom. I will send out a poll shortly. In the evening someday, I will make sure everyone can attend. I'll probably do a 1.5 hour class on Zoom, and then we are in good shape. The midterm, I cannot tell you anything about the midterm yet because I haven't graded your first midterm. So it's possible it will be like last time, or it will be a research paper that you have to read and submit a project on, submit a report on. And I want to grade your midterm before deciding what it will be. I will tell you by Monday latest. Yeah.
Can you go back like 4 pages or something back to that where you
It's more than 4. Back?
Yeah, at the bottom, what's after T? What is that?
What?
At the very bottom.
Yeah.
Oh, really? That's coefficient. Some coefficient. Yeah. Okay, any more questions? Yeah, go ahead.
Do we know when the second midterm is going to be?
Around Thanksgiving. So if it's a paper that you have to review, then I will give you one class off, and you will have the whole Thanksgiving break to read the paper and work through it, you know. And I will give you ample time. But if it's an exam, then I will clarify it by Monday. So don't worry. The final will be in class, that's for sure.